Hi, my name is Ellison Lau. I'm a computer science honors student in UWA, and today I will be presenting my research on generating authentic grounded synthetic maintenance work orders. This research was conducted with the UWA NLP-TLP team with my supervisors Melinda, Michael, and Caitlin. So first off, let's start by understanding what maintenance work orders are. Maintenance work orders, or MWOs, are used in asset maintenance. They're recorded manually by maintenance technicians, such as mechanics and electricians, to document the need for maintenance tasks on all sorts of equipment or assets. They are like doctor notes or prescriptions, but instead of recording symptoms for humans, MWOs document issues and conditions for equipment. This data holds very important information about equipment conditions and the ways that they fail. So, they are used in analysis for informing maintenance strategies. But they are short, unstructured, and very technical. Technical meaning that they contain technical terms, industry-specific jargon, abbreviations, and sometimes also spelling mistakes. But given the important information that they hold, there is commercial interest in training information extraction models to process this data. You may think that this is not a problem since NLP techniques have been advancing recently, but there are several challenges in processing MWOs. This is mainly because they are so technical, and standard NLP techniques are not made to handle technical text like this. But training models from scratch require a lot of training data, which in this domain, this is where we face the problem of a lack of technical datasets. This is because companies that own or operate industrial assets keep this kind of data private, as they contain sensitive information like equipment IDs, etc. So, confidentiality is a big issue, making it hard to release large-scale and shared datasets. So, this is where we turn to LLMs, large language models, which, as we all know, have shown impressive performances on many NLP tasks. There's potential in using LLMs to generate synthetic data in low resource data areas. But one problem with LLMs is that they tend to hallucinate, which means that they sometimes generate content that is factually wrong. This is bad in asset maintenance because a wrong piece of data could lead to fixing the wrong component of an equipment, just like a wrong diagnosis from a doctor leads to treating the wrong illness. So, while LLMs offer a lot of potential, we have to find ways to minimize these hallucinations. So in this research, our objective is to generate and assess authentic grounded synthetic maintenance work orders. Authentic meaning that they look like real MWOs, grounded meaning that they are factually correct in engineering knowledge, and synthetic meaning that they are artificially generated. In this research, the dataset that we are using is the MAINT dataset. This dataset contains work orders that has been cleaned and sanitized to mask any sensitive information. The benefit of using this dataset is that it contains these detailed annotations tagged by engineering experts. These annotations are made up of entities such as physical objects in green, for example, air conditioner or thermostat, and as well as the relations between them, such as the has-part relation. In this example, air conditioner has the component thermostat, and this relationship can be represented by that has-part relation. MAINT also has a deep learning model that is able to annotate other work orders with the entities and relations in the MAINT schema. So, any company can run their data through the MAINT annotating model to structure their data in this format, and then it can then be loaded into a knowledge graph database as shown below. In our experiments, we loaded the MAINT dataset into the Neo4j graph database. This is useful because companies can then go and query the knowledge graph to retrieve information. So for example, how many times have air conditioner thermostats become unserviceable? And you can use cipher queries like this to retrieve that sort of information. Now, I will walk through the pipeline of our synthetic data generation process. In the first step of the pipeline, we extract valid paths by querying for equipment failure relationships from the knowledge graph. To explain this better, let me start by breaking down the structure of MWOs. MWOs typically contain 1. An equipment or its components, 2. An observation of its failure mode, and 3. A maintenance activity needed to be done on an equipment. And using the main entity classes, equipments can be represented by the physical object class, which are in green, and failure events can be represented by the undesirable states, processes, and properties, which are the red, orange, and blue ones. And from that, using a bottom-up approach, we were able to devise what we call paths, which is basically just different combinations of equipment and failure events. There are different types of paths. Paths with just a direct connection, and paths with a middle entity linking them together. And examples of paths here are glass window cracked, exhaust leaking, batteries have no charge, etc. Additional paths beyond what's already in the dataset can also be created using the hierarchical relations of the equipments by substituting them or connecting them together. And at the end of this process, we have a list of around 3,800 valid combinations of equipments and their failure modes, all extracted from the main-T dataset, which alone only had about 1,000 entries. This path extraction step in the pipeline is important because we are extracting valid pairs of equipment and failure events that have already occurred in real-life work orders. And these paths are then used to ground the LLM's output generation to contain correct engineering relationships. Next, we move on to using an LLM. In this case, we use GPT-4o Mini to generate the MWO sentences. We went through a prompt engineering process to find the optimal prompt, and we also used a few-shot learning method in which where we gave the LLM a small set of examples of the desired output. So here is an example of the input prompt. Generate a maintenance work order sentence describing the following equipment and undesirable event. So we give it the equipment word, ignition switch, and the failure term, unserviceable. And then we enforce that it has to use those terms and not to add any new information. This is because we are trying to control what it generates to make sure that it is grounded in real knowledge. Then, we also ask it to keep the sentences concise and direct with an 8-word limit. This is to mimic the short style of MWOs. We also included a blacklist of phrases to discourage the LLM from generating them. This is because these phrases used by the LLMs are not typically used by technicians when recording work orders. They were giving away the fact that they were synthetic. For example, a technician would more likely write valve leaking rather than valve shows signs of leaking. Some of these restrictions were implemented after manual analysis of the LLM outputs from several trials. And here is an example of what the LLM would output. See how it is using the given equipment, ignition switch, and the given failure word, unserviceable. In the last step of the pipeline, the sentences go through a humanization step to make them look like they were written by a human technician. We used rule-based techniques and probabilistic rules to introduce these human-like elements to them. We went with this approach because there is not much research done on making the data dirty. This is because most research usually focuses on cleaning the data, not muddying them up. Contractions had a 50% chance of being introduced, for example, replacing is not to isn't. This is to mimic the informal writing style of technicians. Then we add abbreviations to the sentences, such as air conditioner becoming just AC. This is done because technicians usually like using shorthand notation to document work orders more quickly. And then finally, we simulate some typo mistakes that technicians might make during their data entry process. And here, working is misspelled to mimic a potential typo. Again, the probability of introducing these elements were tweaked and to ensure a balance between having normal work orders and work orders that contain mistakes or shorthand. This is because maintenance technicians are not always consistent with the jargon that they use, and they do not always make mistakes as well. Now, that is the end of our synthetic data generation pipeline, and now we will look at the ways that we evaluated the quality of our synthetic data. The first evaluation method was because we wanted to assess how well our synthetic data was able to replicate real MWOs. So, we conducted a Turing test by sampling 50 real sentences and 50 synthetic sentences, pulled them together, and then shuffled them up. We had 3 subject matter experts do the test, and they were informed about the 50-50 synthetic to human ratio. They then labeled the sentences based on whether they thought it was human or synthetically written. The second evaluation method was mainly to evaluate how grounded our synthetic data is. This evaluation method was replicated from another paper which was also evaluating their synthetic MWO data generated by using grammas. The evaluators were asked to rank the sentences on a scale of 1 to 5 based on 2 metrics, naturalness and correctness. Naturalness being whether it looks like it was written by a human technician, and correctness being whether the relationships between the concepts are plausible and technically correct. For example, can this equipment have this component, or can this equipment fail in this way? Once again, the sentences were pulled and then shuffled to avoid bias. And here, this is the results that we got from our Turing test. It is important to note that the target accuracy is 50% to pass the Turing test because a sentence always has a 50% chance of either being human or synthetic. And in our Turing test, we got an accuracy score of 57%. And this shows that our synthetic data was able to mimic the style of real NWOs, considering how our evaluators, who are very familiar with and often work with these NWOs, were unable to accurately tell them apart. We also got an annotator agreement score of 0.1. This scale was from -1 to 1, where 0 meant that it was as good as guessing randomly. So, a score of 0.1 meant that our evaluators were pretty much just guessing for the most of it. And another interesting point is that we got a higher proportion of human labels, even though the evaluators were aware of that 50-50 ratio. This means that they were subconsciously labeling more as human, which suggests that the synthetic work orders were very similar to the real work orders. And we actually ran a first iteration of the Turing test, but after analyzing where the synthetic data fell short, we were able to identify certain patterns that gave them away. So we went back to the prompt engineering process and implemented those key improvements, such as enforcing conciseness and blacklisting those giveaway words. Now, let's take a look at the results that we got for our ranking test. Here, we can see that the human data scored higher than the synthetic data in both metrics, but also from here, you can see that the synthetic data's correctness score scored relatively highly with a 4.04 out of 5. This means that our grounding process worked pretty well in retaining engineering relationships. An important point to note as well here that even the human data did not achieve a perfect score for the correctness. This highlights that even real data is not always perfect. We also noticed that the reason why many of our synthetic sentences scored poorly for correctness was because that the original Menti dataset had inconsistencies, causing the synthetic data to be wrong. But overall, from this ranking test, we were able to say that our synthetic data is 86% natural and 95% as correct as the real data. Going back to our research objectives, which is to generate and assess authentic grounded synthetic maintenance work orders, And by using prompt engineering, few-shot learning, and the humanization steps, we were able to create authentic synthetic maintenance work orders that reflect the nature of real MWOs. And this is reflected by the 57% accuracy in the Turing test. This 57% accuracy in the Turing test that we got is really impressive considering how the synthetic data was really able to confuse our subject matter experts. And by using the valid paths that we extracted from the main T knowledge graph in the generation process, we were able to ensure that the LLM output was grounded in real engineering knowledge. This is reflected by the correctness score of 95% in the ranking test. So, overall, we were able to propose a novel method of grounding synthetic data generation by LLMs using knowledge graphs and annotated datasets. With this synthetic data generation plus grounding process, companies can then go and create their own synthetic training data for training and fine-tuning their own datasets and training their own models, all internally without exposing any sensitive information. And also, in this way, we are able to obtain both a cleaned version and a non-normalized version of the synthetic dataset. This is useful in situations where you need to train models to handle a diverse real-world variations. There are a lot of areas where synthetic data can be applied to, and synthetic data generated using this pipeline is already being used in a fellow honor student's research project. So there's a clear benefit here. Something to note is that the grounding process is reliant on the items and relationships expressed in the original dataset and the annotation schema. This means that our process is reliant on the original dependency being correct and complete. Another sort of limitation of this work is that GPT is non-deterministic. This means that it would be really hard to replicate the exact same results from this research. As for future work, the work done here helped to find some incorrect data in the original Mainty dataset. This happened while we were analyzing our evaluation sample sentences. So this means that there can be a feedback loop into fixing the erroneous data in the Mainty dataset. Additionally, there is potential to evaluate the utility of the synthetic data by using it as training data to train machine learning models and seeing how well it performs compared to models that were just trained on real data. And that is it for me. Thank you for listening. These are the references.